Hello again. In this week's lecture, we're going to talk about the theory of traffic flow. We're going to cover some of the fundamental modeling approaches for traffic flow modeling and simulation. A couple of acknowledgements again. Thank you, Prof. Washburn, Bertini, Van Lint, Shiva Cody, and Ramsey for some of the content that I have in my slides that are borrowed from your work. So in the previous lecture, we talked a little bit about the relationship between traffic flow fundamental variables like the flow density relationship or speed flow relationship, speed density relationship. But we didn't really talk about mathematical formulations of those relationships. So let's start with a very, very simple model. So imagine we're looking at the speed density relationship. If you remember from previous slides from last week, the speed density relationship, if you plot it with real data, it will be very scattered. But we can approximate that relationship with a very simple linear relationship. And this is called actually Greenshields model. So Greenshields model is one of the very first models in traffic flow, which again, it's very simple. It assumes a linear relationship between a speed and density. Today, because of a lot of real data that we have access to, we know that this is not necessarily the case. The relationship between the speed density is not really exactly linear, but again, it's a model. It has its own properties. It has its own advantages and disadvantages. And it's an approximate of that relationship, as I said. So here, let me find my pen actually. I wanted to draw on the, okay, I found my pen, yes. So U represents a speed, so y-axis is U. UF is the free flow speed. It's this point where the density is 0, speed is maximum. K represents density, and it's shown on the x-axis. And Kj is jam density, which is basically the maximum density we can get when the speed is 0, when traffic is actually at the gridlock level, and everyone's stopped, what would be the maximum density? So that's Kj. So this formula is basically the equation for this line with the intercept of UF on the y-axis and an intercept of Kj on the x-axis. So U would be UF 1 minus K over Kj. This is also called Greenshields model. We can also derive an equation for flow density relationship. This is also called Greenshields model. All of these models that I'm now showing you are Greenshields model. So very similar to the linear relationship that we had for speed density, we can also derive a parabolic type relationship for flow density. And again, as I said before, this is only an approximation of the actual relationship, because if we plot real data on top of this model, we'll see that it does not necessarily match or follow real data. But again, it's a reasonable approximation. So x-axis here is density, K. Y-axis is flow or Q. This is Kj, jam density. Here is maximum flow or capacity. We can also call it Q cap or QC. And in the Greenshields model, one interesting property is that you see this Kj, and this is maximum flow. So maximum flow happens at a density that is associated with the capacity. So this K cap can be called density associated to the capacity, right? So at what density we'll have maximum flow, or at what density we can reach capacity. And one of the interesting and nice properties of Greenshields model that makes it a bit more attractive is that the density at capacity is actually equal to half of Kj. This relationship, this property that K of capacity, density of capacity is always half of the jam density, only holds for Greenshields model, okay? So if we are using another model, this wouldn't apply, okay? So K cap is equal to half of Kj. And again, this relationship, this equation you see here is actually the equation for this parabolic shape curve, which says flow is equal to the free flow speed. So this UF again is free flow speed, K is density, and Kj is jam density, as I introduced before. So we'll have Q is equal UF multiplied by K minus K power 2 over Kj, which represents this parabolic shape model here. We can also look at a speed flow relationship, right? Because all these speed flow density are related, as we covered and talked about in the previous lectures. And again, this also looks like a parabolic type shape, but it's not exactly parabolic because it's actually the other way around. It's not, sometimes it's not called a mathematical function because for every flow we'll have two speeds. But anyways, if we want to come up with an equation for this curve, where x-axis is flow and y-axis is speed, we can derive this equation saying that flow is equal to jam density multiplied by u minus u power 2 over uf, and uf is again free flow speed. So look, as long as we have kj and uf, as long as we have jam density and free flow speed, we can use this equation to convert a speed to flow or flow to a speed. In the previous slide, same thing. As long as we have free flow speed and jam density, we can use this equation to actually find out what would be the flow if density is at whatever number. We can convert density and flow. Same thing with the initial one. As long as we have free flow speed and jam density, we can convert density to a speed. And now if you put all these three relationships next to each other, this was the density flow relationship, this was density speed relationship, and this is flow speed relationship. These are called traffic flow fundamental diagrams. And again, this is another very fundamental and basic modeling concept in traffic flow. And it's widely used. It's very fundamental. We use these relationships in many applications when it comes to calculating speeds, when it comes to calculating flow. We use all of these models. And behind some of those commercial traffic simulation softwares that you'll see in this course, or you've already seen, these fundamental diagrams are in play. So these are called traffic flow fundamental diagrams, the relationship between flow density, and speed flow. And all of these models that I covered in these slides were called Greenshields model. We have a couple of other models, which doesn't necessarily follow the same equation. So for example, the flow density relationship, Greenshields model assumes it's a parabolic shape, but there's another model that says this relationship is triangular. Or it looks different. These are all single regime models, but we could have a dual regime model where For example, we have a free flow, we have an uncongested branch, and then with some discontinuity, we have another curve on the right. So this is called the dual regime model because we have this discontinuity between the uncongested and congested model. But anyways, there are many different models, but here we have only focused on Greenshields so far. So let's have a look at an example of how we can actually use Greenshields model in a practical problem. A section of a highway is known to have a free flow speed of 100 km per hour and a capacity of 3,300 vehicles per hour. In a given hour, 2,100 vehicles are counted at a specific point along this highway section. If the linear speed density relationship holds true here, estimate the space mean speed of these 2,100 vehicles. So when we say if the linear speed density relationship holds true, what does this mean? This actually means we're going to go with the Greenshields model. Now let's write down all the information the problem is providing us. So it says free flow speed is 100. Make sure you also put down the units because we want to make sure the units are consistent. And if there is a need for converting the units to something else, we don't want to miss that. Capacity or Q cap is 3,300 vehicle per hour. At some point in time, Q is equal to 2,100 vehicle per hour. And we want to estimate the space mean speed of these. So we want to know, so we have UF and Q cap. We have the capacity and we have the free flow speed. The question is asking us when flow is equal to 2,100 vehicle per hour, what would be the speed? To get that, we can actually just refer back to the Greenshields model where we can convert speed and flow, speed to flow, and we can see that we need to use this equation, to use this model, we actually need jam density and free flow speed. So if I go back to my problem, I have the free flow speed, but I do not have jam density, right? So let's see. So let's first write down the Greenshields model. So Greenshields model, we're saying Q is equal Kj, U minus U power 2 over UF. So I have UF is 100, but I don't have Kj. How can I get Kj here? How can I get jam density here? So let's have a look at the, let's plot some of the fundamental diagrams here schematically first. Let me erase this for now, so I have enough space to draw the fundamental diagrams. So if I plot the fundamental diagram relating density and flow, again, we're going to go with Greenshields model, so it's a parabolic shape, right? And I know the Q cap, so this is Q cap, which is 3,300. Let's also write K cap here and Kj. I can also draw the speed flow relationship. So this would be speed, this would be flow. I have the UF, so this is UF, right? Which is 100 kilometer per hour. And again, I have this Q cap, which is 3,300. So we said in the previous slides that one of the interesting properties of Greenshields model is that K capacity is always half of Kj. So if I somehow find this K cap, and if I just multiply it by 2, I would be able to get Kj, right? But how can I get K cap here? So another interesting property of the Greenshields which can be seen on this UF, which can be seen on the right diagram here, is that the speed associated with the capacity, let's also call it U cap, is also half of UF. So the speed at capacity, in this case, would be 50 kilometer per hour, right? Because it's half of this the free flow speed. Again, I want to highlight here these K cap equal half of Kj and U cap equal half of free flow speed only holds true when we're working with Greenshields model. If you're working another model, this may not necessarily holds true. So now that I have the speed at capacity and I have the actual Q cap, I can get K cap, right? If I use the traffic flow fundamental identity, which is Q equal KU, right? So if I want to get K cap, I just need to say the flow at capacity or capacity equal to the speed at capacity. So I had 3,300 over 50. And if I calculate that, I'd get K cap would be equal to 66. So that would be vehicle per kilometer. So that's my K cap. And again, because K cap is equal to half of Kj in this case, so Kj would be 66 multiplied by 2. It would be 132 vehicle per kilometer. So I somehow found jam density. Now that I have jam density, I can actually use the Greenshields model to actually calculate the speed when flow is equal to 1,200. So if I write this Greenshields model again here, so it would be Q is equal to 132 U minus U power 2, and the free flow speed was 100. So I have this relationship now, and the question is asking estimate the speed when flow is equal to 2,100. So if I just replace this Q here with 2,100, and if I solve this equation, I would be able to get U, right? So if I want to draw that on the fundamental diagram, so 2,100 is somewhere here, right? So 2,100. But what is interesting here is because of this parabolic type shape relationship, if we solve this equation, we're actually going to find out two values for this speed. You see, for the flow equal to 2,100, I can either find this speed or this speed. So one of them is in the uncongested regime, the other one is the congested regime. So how does it, how can we interpret this? So look, if we are in the uncongested regime, the road is not very crowded. The flow is relatively small, lower than capacity. So speeds are going to be high. So if I find a speed, if I find this point, when I solve this equation, one speed that I get will be on the uncongested branch. But when the road is congested, there's too many traffic. So the flow is low, not because there isn't enough cars on the road. The flow is lower than capacity because there is congestion on the road. So in the first point on the uncongested branch, the flow is low, but the speed is high because it's uncongested. But the other point on the bottom, the flow is lower than capacity because it's congested. There's enough car, but there's a queue on the road, and the speed is low. So I will get two values for U if I find this equation, and both of them are correct. One of them relates to if flow is 2,100, and if we are in the uncongested regime, we'll have the higher speed. If we are in the congested regime, we'll find the lower speed would be the correct answer. So let's actually try to find the answer to this equation. We want to actually find the root of this parabolic shape, polynomial equation. So if I go to MATLAB, okay. So here, let me get rid of this tab. So here, to find the root, I need to define a function. And my function is actually my Greenshields model, which was kj multiply u minus u power 2 over free flow speed minus 2100. And if I find the root of this equation, I can use f0 and I need to give it an initial answer, right? For example, I start with 0 as the initial answer. Let's see what it gives me. So 1 u would be equal, 1 speed would be equal to 19.85 kilometer per hour. And if I change the initial answer to actually find the other root of the equation, for example, if I give the initial answer to 100, it will find the other root, which is equal to 80.15 kilometer per hour. So you see, I get one speed which is low and one speed which is high. So obviously, this speed equal to 19.85 is from the congested regime when the flow was equal to 2100, while the speed equal to 80 is coming from the uncongested regime and the flow was still 2100. Let's have a look at a second example. Imagine a section of highway that has the following flow density relationship. What is the capacity of the highway section, the speed at capacity, and the density when the highway is at 1/4 of its capacity? So this is again a parabolic relationship, right? So if I draw the traffic flow fundamental diagram, I have K here, I have Q here. I have a parabolic curve here. I have Kj, I have jam density, I have capacity here, I have K at capacity, etc. So the question is asking us, what is the capacity of the highway section? What is the speed at capacity? What is the density when the highway is at 1/4 of its capacity? So how can I answer this question? So first of all, how can I get the capacity here? If I have the Greenshields model, if I have this parabolic relationship, if I want to get that maximum point, so you see capacity is at the maximum point of this curve. So if I want to get that maximum point, what should I do? I can take the derivative of this equation, make it equal to 0, and I will be able to get that maximum point. So if I go with dq over dk and make it equal to 0, I would be able to get that capacity. So that would give me 50 minus 6 power 2, sorry, not power 2, multiply by 2 equal to 0. And this will give me the density that I need, the density at capacity. So if I solve that, let me quickly calculate that. So K would be equal to 160.26 if I haven't made any mistake in my calculation. So that's K cap, the density associated to the capacity. But the question is asking for the capacity itself, actually. So I need to put this K cap into the back to the equation and calculate the flow. So flow would be 160.26 minus 156, 160.26 power 2. And if I calculate that, that would be equal to, so Q cap would be equal to 4006.4 if I haven't made again any mistake here. So that's the capacity. The question is also asking us about the speed at capacity. I have the density at capacity, I have the flow at capacity, so I can easily use the traffic flow fundamental identity Q equal KV to calculate the speed at capacity. So speed at capacity would be Q over K. And if I calculate that, that would be equal to 25. So I have the speed, and the question at the end is asking find out the density when the highway is at 1/4 of its capacity. So Q is equal to 1/4 of Q cap. So it would be 1/4 of 4,006.4. So if I calculate that, that would be, so Q equal to 1,001.6. So that's the flow at 1/4 of its capacity. We want to know what is density. So we just need to put this Q into the Greenshields equation. So it would be 1001.6 is equal to 50K minus 156K power 2. And if I find the root of this equation, I'll get the K that I need. And again, I will get two Ks, right? I will get two values for density because this would be the 1001.6. So I would get one density here and one density here. So let's do that also in MATLAB again. To find the root of this equation, if I write it down here, I want to find the root of this equation. So I say fx is equal to at sign x, which is I'm defining the variable in my equation. So it would be 50x minus 156 x power 2 minus 1001.6. So that's my function. And if I want to find its root, if I give 0 as the initial guess for the solution, so 1K, so the first solution would be density is equal to 21.47. And if I give it another initial guess, with 200. Yes, so the other one would be K is equal to 2990426. If I go back to my slides, so what is jam density here? If the density at capacity is 160.26, jam density would be double than the K at capacity, right? So we just need to multiply this 160 by 160 0.26 if I multiply by 2. So jam density would be Kj here actually would be equal to 320, right? So and the flow that and the density that we calculated, the second density we calculated as the root of that equation was 299. I just want to make sure it is lower than Kj to double check that the answer is correct. So in this case, it would be 1K is actually 21.47 and the other K is actually 299, and while Kj was is actually 320. So that's how we use Greenshields model to actually calculate the speed density at any traffic state